In this video we're going to show you how to perform some simple packet analysis with Wireshark. Wireshark has pretty much become the standard in packet capture and protocol analysis in the networking industry. You can use it to capture packets of the network for analysis, you can use it to identify and analyze the various networking protocols, or to just quickly identify the source and destination of traffic if that's what you're looking for. It's important that you know the basics of Wireshark before getting into the analysis of OpenFlow. So we're going to start with a brief overview of how to investigate the protocols and traffic in a series of videos. I'm going to start the video with assuming that you already have Wireshark installed and that you grasp at least the basic concepts of computer networking. First, we're going to start with a simple ICMP echo and look at the contents of the Ethernet frame and the IP header. Let's just get started here. Here we have a frame header that includes the destination MAC address and the source MAC address. Notice that the type is labeled 802.1q virtual LAN with a type of 8100. This means that the frame has been tagged with the VLAN identifier, which can be seen on the next line. You don't really need to memorize this, but you should at least know what you're looking for. If the frame was not tagged with a VLAN ID, for example, it would have a type of 8000. So if we expand the 802.1q field, we see that we have a priority field set to 0, which is set as the class of service, or COS. This is being set as best effort. It'll either have a value between 0 to 7, 7 being the highest priority. ICMP is really not all that time critical in comparison to video and voice, so it usually gets a really low setting. Next is the CFI, which is used to set the drop precedence of the frame. And then finally we see the 12-bit field that identifies the VLAN ID, which in this case is VLAN 123. This is another helpful troubleshooting skill when investigating your traffic, so you should be able to know where to find your VLAN tags in your Ethernet frames. Alright, so let's go ahead and jump in and take a look at the IP header. The IP header is comprised of 14 fields, each packed with the most significant bits first, starting at 0, if you're reading left to right too. The first field we see is the version, which we can see here. See it's a IPv4 packet. And next we see the header length, which defines how long the header is going to be. The next field is known as the DSCP, or the Differentiated Services Code Point field, which don't get me to try to say that 10 times fast, I'm just not going to do it. This field was originally defined as a type of service field, but now it's defined by RFC 2474 as the Differentiated Services field, or DiffServ for short. Technologies that use real-time data streaming make use of the DSCP field, like VoIP for example, or interactive video. It's a 6-bit field that identifies the QoS properties of the packet. You also see the explicit congestion notification, or ECN field, next. This field is usually used to notify the network of any type of congestion, but it's used when both endpoints support it and are willing to use it. Next we'll see the total length field. This field defines the entire packet size, including the header and data in bytes. The smallest length packet is 20 bytes, which is comprised of a 20-byte header and 0 bytes of data. The maximum sizes can be 65,535 bytes. Again, not something you need to memorize, but it's just good to know. The next field we come across is the identification field. This field is primarily used for uniquely identifying fragments of an original IP datagram. Some experimental work has suggested using the ID field for other purposes, such as for adding packet tracing information to help trace datagrams with spoof source addresses. But as you can see here, the value is set to 6. If we click on both of these, you can notice that they're both 6, and then we can see the next pair down has a different value associated to that as well. Next field in the IP header is called the flags field. This field is comprised of 3 bits which are ordered from high to low. The first bit is reserved and must be set to 0. This bit actually has some humor behind it, as it was proposed as an RFC in 2003, written by a man named Steve Bellavin. It was being called the evil bit. The idea behind it was that if you had any malicious intent with these packets, you would set it to 1, so that way computer security engineers would be able to catch that traffic and just ignore those messages, making their jobs really easy. You can read about this in RFC 3514. It's a pretty funny read, but let's just get back to the rest of the header fields here. If the second bit is set, the DF bit, and fragmentation is required to route the packet, then the packet is dropped. This can be used when sending packets to a host that does not have sufficient resources to handle fragmentation. For unfragmented packets, the third or MF flag is not set. But for fragmented packets, all fragments except for the last have the MF flag set. The next field we see here is called the fragment offset, which is 13 bits long and specifies the offset of a particular fragment relative to the beginning of the original unfragmented IP datagram. The first fragment has an offset of 0. The time to live field is next. It's also called TTL for short. I'm sure a lot of you people have heard this already. It defines how long the packet will live in a value known as hops. This number decrements with each hop it takes through the network or each router that it hits. When it hits 0, the router will discard it and send an ICMP time exceeded message back to the sender. Traceroute uses this to display the routers in a forwarding path that can be used for troubleshooting. The reason why you want to decrement this and have it die is if there's some type of routing loop or the packet's looping around the network, you don't want it to go infinitely. The maximum hop count you can have is 255, but they recommend you set it to 64. The next field we come across is the protocol field. The Internet Assigned Numbers Authority, or IANA for short, maintains a list of protocols defined in this field. For example, in this packet, the protocol is ICMP. Another thing, you don't have to memorize, but knowing where to find this is very important. Next, we have the header checksum, which is used for validation the integrity of the data contained in the packet. For example, this checksum will have to be recalculated if the TTL field in the packet is changed. It's a hash value that gets generated that can be checked against to make sure that the data hasn't been corrupted or tampered with. For more information on this calculation, you can find it in RFC 1071. And next we come to the most complicated field in the entire packet. It's the source and destination address. Here at the bottom of the trace you see more specific protocol information. For instance, this shows that this ICMP message was a request and that this one was a reply. You can also find the time it took to reply in this field here. And that's basically it. Thanks for watching. If you can find some time, I would recommend to play around with Wireshark and get very familiar with how it works, how you can filter. I would recommend visiting www.wireshark.org to get some sample files to play with, or even pick up a book called Practical Packet Analysis by Chris Sanders. This book helps you lab out and play with different types of traffic, and it really gets down to the nitty-gritty. Again, thanks for watching. Hope this is very informative.